this is a continuation of the problem that we did in class. Again, we have a 2 millimeter diameter bead that's charged with an excess of negative charge, negative 1 nanocoulomb to be exact. This time we have an electron that's given some initial velocity, sending it towards the bead. This electron is going to get to a certain point, which we'll call F. At that point, it's going to turn around or reflect and move back the direction it was already going. So at this point, we know that the velocity would have to be 0. Now, looking at the situation, it has some initial velocity. At this point, when it's far away and has that initial velocity, the potential is going to be 0, and we're going to assume that the distance it's at, so x initial, is infinity. That's where the far away part comes from. Now, if this electron is moving towards the negatively charged bead, that means that the potential energy is increasing. Since it's 0 when it's far away, that means that the final potential energy is going to be greater than 0. So by looking at the situation, we can see whether or not we need to have a positive or negative potential energy. So let's go through and break down the different energies involved in both cases. Before, we've got some kinetic energy, so 1/2 mass of the electron times the initial velocity squared, plus the potential before, which is 0. This is going to equal the after case. Our kinetic energy is 0, since our final velocity at this point, F, is 0. But we do have some final electric potential energy. So, rewriting this, we've got the kinetic energy of the before equal to the potential energy of the after. Plugging in for our potential energy due to 2-point charges, we've got K times the charge of the bead times the charge of the electron over the distance between the bead and the electron at point F. So that means that we're assuming that the center of the bead is x equals 0, and that this point F is the final position. So what is this final position? Well, given the quantities in the problem, we are looking at the radius of the bead, which is 1 millimeter. The diameter is 2 millimeters, the radius is 1, plus the extra bit off the surface of the bead, which is 0.1 millimeter. So that means we're talking about 1.1 millimeter. Alright, we can go ahead and solve our equation for the initial velocity. That's what we're looking for here. So I'll multiply both sides by 2, divide both sides by the mass of the electron, and then square root the entire quantity. Plugging in my numbers here, K is 8.99 times 10 to the 9th newtons per meter square, Newton meter squared per coulomb squared. Mass of the electron you can look up is 9.11 times 10 to the negative 31 kilograms. The charge on the bead was given, that's 1 nanocoulomb, so 1 times 10 to the negative 9 coulombs. The charge on the electron you can look up, that's 1.6 times 10 to the negative 19 coulombs. And our distance here we'll need to convert to meters, that's 1.1 times 10 to the negative 3 meters. Plugging all of that in, we find that the initial speed must be 5.3 times 10 to the 7 meters per second. So about 53 million meters per second. This thing is definitely moving quick.